Okay, so right now I'm going to be presenting number 1 from Wednesday's assignment, forces and friction. This is question number 1. A little boy pushes a 12-kilogram box of library books with constant velocity along the sidewalk by applying a horizontal force of 96 newtons. Draw a free body diagram of the box, calculate the weight, normal force, frictional force, and coefficient of friction between the box and the sidewalk. Okay, so a lot of stuff to untangle there. The first thing we have to understand is, what does it mean to say draw a free body diagram? A free body diagram is just simply a diagram that shows all the forces acting on an object and in which direction they go. So you're really just drawing the force vectors. So here we have the box, and let's draw in some forces. The little boy is pushing this box at 96 newtons, so here would be one force, and we can label this vector as 96 newtons. I'm just going to write in here, this is the mass of the box is 12 kilograms. Now we also have to draw in the other forces, and so we have to understand the physics here of what's happening. Well, the box has a weight, and the weight is always directed downward, so there is a force going like this. This is the force of gravity, and the way you calculate the force of gravity is mg, and that comes from notes. But the force of gravity is mg. Okay, that's not the only force, however. There is the force, Newton's third law. If the box pushes down on the floor pushes up on the box. So there is a normal force component to this. Looks like that. However, that is not the only force acting on here. In this case, there's friction between the box and the sidewalk, and friction always acts along the points of contact, and it always opposes motion. Friction never helps motion, it always opposes motion. So we're going to draw that force down here like this, and we'll call this force of friction. Since the box is sliding, it's kinetic friction technically. It's not any other type of friction. It's not static friction or something like that. If the box was still, it would be static friction. But anyways, okay. So we're going to calculate the weight. Well, the weight is the force of gravity, and that's equal to mg. So when we solve this, actually, you know what, I'm going to do this without numbers just to save time on the video. So calculate the weight. So this will be weight. Again, remember the weight is the force downward due to gravity, and that's mg. So this would be whatever 12 times 9.8 is. And of course that would be in newtons, because weight is a force. Right? So this is a really important idea, is that the mass is in kilograms, the weight is in newtons. So sometimes problems will give you instead of giving you the mass of the object, they'll give you the weight. And you can always tell because they'll give it to you in newtons rather than kilograms. So that takes care of the weight. The normal force. Okay, this is an important idea. The normal force. The normal force is the third law paired to the weight. Again, the box pushes down on the floor is going to push up on the box. But here's the key. Is the box accelerating in the y direction? Right? This box is not starting to accelerate upward, it's not accelerating downward through the floor. So that must mean that these two forces cancel each other out. So the normal force in this case, the normal force must equal the force of gravity. And again, this is super, super important because it's not accelerating in the y direction. Therefore, these two forces must equal 0 to give an acceleration of 0. So if the normal force is equal to the force of gravity, and we already figured out that the force due to gravity, the weight, is 12 times 9.8, well, guess what? It's going to be whatever 12 times 9.8 was, some number newtons. In this case, it's probably best to give the magnitude of the number and not worry about whether it's a plus or a minus value. It's best just to give the magnitude. Okay, so now we covered the weight, the normal force. All right, frictional force. This one is going to take a little bit more time, not a ton. But the key right here is the words, he's pushing the box at a constant velocity. So that is absolutely crucial to this problem. Remember that forces cause accelerations, and if there's no acceleration, that means that the net force must be 0. So in this case, just think about it logically. The kid's pushing with 96 newtons degrees this way. The frictional force opposes that. And the net result of that is to have a constant velocity, which means that this box is not accelerating. Now you know that the pushing force must be equal to the frictional force. So if the pushing force is 96, the frictional force must be negative 96 newtons. And again, this is super, super important. It's because it's a constant velocity. So your eye should always be looking for, whenever you're doing a problem, is this object moving at a constant velocity? If you see constant velocity, forces must be equal. All the frictional forces and opposing forces must be equal to all the sort of applied forces. And then they must be, the net result of that must be zero acceleration, because that's what constant velocity is. If this force was greater than friction, this thing would be slowly accelerating. It would be speeding up. If the frictional force was greater than the pushing force, it would be slowing down. So again, constant velocity. You don't even have to calculate this, at least this particular question. The frictional force is negative 96 newtons. Frictional forces are always negative forces, because I don't know of a single type of friction that speeds something up. And I'm just talking to my iPad, but do you, iPad? Do you know of any frictional forces that speed things up? My iPad is silent because he knows the answer. The answer is no. So frictional forces are always negative forces. That takes care of that one. And now we just need to get the coefficient of friction. Okay, so this is a little bit more interesting in the question. Remember that all frictional forces are calculated by mu times the normal force. Right? This mu is the coefficient of friction, and sometimes it's mu sub s for static friction, sometimes it's mu sub k for kinetic friction, mu sub r for rolling friction, and yeah, so on. In this case, it doesn't really matter, but technically it's kinetic friction because the object is moving. All right. Well, the normal force in this case is equal to the gravitational force. We've already said that. So this right here, this value, it should be taken care of. The frictional force in this case is negative 96. That should be taken care of as well. So the mu, the coefficient, is really just going to be the force of friction divided by the normal force. So in this case, this would be negative 96 all over whatever 12 times 9.8 was. I don't know what that was. I bet you do by now. So I don't know what the number is, but I want to tell you something right now, which is that mu's are always positive. Coefficients of friction are always positive. So mathematically, you'll get a negative, of course, because you have a negative divided by here. Your job is to, don't think like a mathematician where you're like so precious, those negatives are so precious and indispensable. Think like a physicist and understand that I can just drop the negative because it's a coefficient. The coefficient is basically just an indication of how frictional two surfaces are, and I'm just going to drop it. So in this case, we're going to drop the negative. So whatever this number is going to be your answer. And of course, there's no unit. It's unitless because this is a coefficient. Now let's put on our mathematician hat. Coefficients are unitless. They don't have any dimensional components of them. And so you're just going to get a number. And usually that number is between 0 and 1. But sometimes on really, really, really sticky objects, you'll get a coefficient greater than 1. But usually it's between 0 and 1. Okay, that is how you solve question number 1. And thank you, iPad, for being a great audience.